Okay, folks, welcome back. Good morning to you. As you know, you have an exam. It's open and available in the testing center today. It is 20 questions long. Average duration tends to be around 2 hours with some standard deviation. So figure out, you can sort of calibrate based on how long you typically take on an OChem exam. Each question is worth either 10 or 9 points. 183 doesn't divide nicely into 20, so 3 of the questions are worth 10, the rest are worth 9. And we'll have a chance towards the end of the class to answer some additional questions that you might have. What we want to do today is focus in on some biological examples of nucleophilic acyl substitution reactions. And the chemistry itself is not going to be new. It's going to involve attack of a nucleophile on a carbonyl carbon. It's going to involve getting a tetrahedral intermediate and then kicking off of a leaving group. We call that, as I've said, a nucleophilic acyl substitution reaction or acylation. But the players are going to be different. They're going to be structures that you haven't seen before. Some of them are going to be a pain to draw. You want to sort of experience 2 emotions today during class. Number 1 is overwhelm at the structures that we're drawing. You're going to ignore that one, and then you're going to experience boredom because the actual chemical steps are going to be pretty similar to what you've seen before. Combined together, overwhelm and boredom equals confidence. You're surprised by that, but it's true. If you can, at the same time, be overwhelmed by structural complexity, but then know how to deal with it in a way that's similar to something you've already seen, that's power in biochemistry. So let's dive in. We're going to talk about, first, beta-lactam antibiotics, what they are and how they work. Some of you aspire at some point in your future to have the authority to prescribe things to people, including beta-lactam antibiotics. So here's where you're going to learn what some of those things do. So I'm going to draw one for you. Understand as we draw structures, the point is not to memorize a structure. There will be days for that. They are coming in chapters 23 and 24 and so on, but now is not that day. So here is amoxicillin. Some of you have probably taken this before. The key portion of amoxicillin is this 4-membered ring with a nitrogen and a carbonyl carbon. We'll fill in the rest of the details in a little bit, but I'm going to identify the carbonyl carbon, the alpha carbon, and the beta carbon. Cyclic amides are called lactams for whatever reason, not sure why, but cyclic amide is a lactam. A beta-lactam is a cyclic amide in which the nitrogen is attached to the beta carbon. So beta-lactams necessarily are 4-membered ring containing compounds. Now let's just pause and think about that. Here's the carbonyl carbon, here's the carbonyl oxygen. That nitrogen is going to be attached to something else. The key feature of beta-lactams is ring strain. Think about that carbon. We would normally say that carbon's sp2 hybridized, meaning its bond angle should be 120. In a square, it's constrained to be somewhere around 90. So that's considerable distortion from the ideal geometry, and that has some consequences for the reactivity of a beta-lactam. Let's fill in some of the other details for amoxicillin. There's a sulfur here. There's a 5-membered ring here that connects to the nitrogen. 2 methyl groups there because why not? And here is a carboxylate group. We won't worry about how beta-lactams are synthesized. They come from amino acids, but that is a story from another day, for another day. Here's a nitrogen, and then attached to that nitrogen is another amide bond, an ammonium group here with a positive charge, and all of your nightmares together in one molecule, a benzene ring. All right. This is amoxicillin. Now, one of the interesting features of amoxicillin is it has 2 amides in it, but one is more reactive than the other. The reason for that is this amide is not acyclic and it's not involved in ring strain. Amides are normally quite stable. Amides are normally not very good electrophiles. They're pretty far down our list of carbonyl compounds in terms of reactivity. That's different for the beta-lactam. The ring strain makes it more reactive, except we can't spell reactive when we're writing it. Reactive, all right, there we go. That's amoxicillin. Now let's talk about what it does and how the ring strain is involved. Before we do that, normally you would think of a nitrogen as being not a good leaving group. If it left as a negatively charged nitrogen, that's a terrible leaving group, but the thing that's going to help make that a good leaving group is if it left. If a nucleophile attacked this carbon, if we got a tetrahedral intermediate and the nitrogen left, leaving would relieve ring strain. And so that's going to pay for, to some extent, the badness of that nitrogen leaving. Okay, questions so far about the beta-lactam? Yes?
N is typically not a good leaving group, but it's going to relieve rings.
It's not a good leaving group normally. In this case, because of the strained four-membered ring, it can be. Because if it left, and I'll show you this later, if it left, this bond is going to be broken and the strain will be relieved in the four-membered ring. Okay. Now get ready, because we're about to draw something. It'll be in the notes, so if you don't get it all down, that's fine. I, in the past, have just pasted it like a slide and expected you guys to just look at it and not worry about drawing it. I'm beta testing something new today. We're actually going to draw it. If you hate it, you can let me know, and maybe we'll do something different next time. So, beta-lactam antibiotics inhibit bacterial cell wall synthesis. And so to understand how this happens, you need to have just a little bit of knowledge about bacterial cell wall synthesis. We're not going to do the full treatment of this. I've done it before in the class, and it mostly resulted in anger. So we're avoiding that by, I hate you, right? I have the high ground, Anakin. You underestimate my powers. Yeah. This is the end of you, my master. Okay. You know what? Star Wars has never been known for the excellent writing and dialogue. It's mostly about the laser swords and the starships. So, yeah. Okay, so there are two six-membered ring carbohydrates linked together in this fashion. On these carbons are two nitrogens, and those nitrogens are modified with acetyl groups. I'm going to abbreviate one of those acetyl groups as AC. Okay, that's the abbreviation for those things. To highlight that, that's not an important part of the structure, so I'm not going to generate a key for that. There are hydroxymethyl groups here, and then there are OH groups here. This is bacterial cell wall peptidoglycan. It's called a peptidoglycan because it's got a carbohydrate portion, which I've just drawn for you here, and then branching off of this oxygen is a peptide portion, which is made of amino acids. Now, again, don't memorize this. We're going to draw it just so you have it in your notes so that I can illustrate what bacterial cell wall synthesis looks like, and so you can understand what the beta-lactam antibiotic does. So there's going to be a chain of 5 or 6 amino acids here. So get ready. That OH is attached to a carbon that looks like that. Here's the first amide bond. There's a methyl group there. Here's the second amide bond. There's a carboxylate there. There's the third amide bond. Oh, you don't mutter yet. We're not even close to done. You got to save your anger for when it's appropriate. Alpha, beta, gamma, delta, epsilon, nitrogen. There's more. Of course I don't have it memorized. Why would I memorize this? Okay, we're almost done. Okay, there it is. So to understand what's going on here, we need to first have an idea of what nature's trying to do. Here is a carbonyl carbon and an oxygen, and here is a nitrogen, and we'll call all of this our proposed leaving group. What nature wants to do is, what I've shown you is one subunit of bacterial cell wall peptidoglycan. And it's a repeating subunit, so there's tons of these in 2 carbohydrate units all in a line. At the end of this nitrogen, the R group that I didn't tell you about because I wanted to spare your sensibilities, is a nucleophile. And what biology wants to do to reinforce the bacterial cell wall, are you ready? Is to have a nucleophile here attack this carbonyl carbon to generate a tetrahedral intermediate. Now, that reaction isn't very favorable because this is not a very good leaving group. So nature needs an enzyme to catalyze that reaction. But after the enzyme does its job, what you're going to see here is there will be, the leaving group will have left, and there will be a new bond. Don't worry about getting all of this down. You can look at the video, and in any case, we're going to focus in on what the beta-lactam antibiotic does. In the end, there will be a new bond between the nucleophile and that carbonyl carbon, and that cross-link between the 2 bacteria peptidoglycan units makes the cell wall more stable, more strong. It's like adding struts in across beams in a building, okay? So that's what nature wants to have happen. That's what the enzyme is supposed to catalyze. All right? Now, I'm going to erase what we just did and go back to the peptidoglycan. And I'm going to show you a Pac-Man cartoon of the enzyme. You thought there was actually going to be animation. I just mean I'm drawing the enzyme, okay? Sorry about that. The enzyme has a nucleophile in its active site. It's an alkoxide. Probably the enzyme had a group in that alkoxide first. It used to be an alcohol, then probably the enzyme deprotonated itself. There are groups in the enzyme active site that can do that. And this is the nucleophile. This enzyme is called glycopeptide transpeptidase, and it's supposed to do the reaction I just showed you, which is a transpeptidase reaction. And for fun, because Pac-Man, we'll just color this orange, okay? So the function of the enzyme, what I showed you is the end goal. I'm going to only give you the first step in the enzyme mechanism that catalyzes this reaction. The enzyme is going to come along and it will attack the carbonyl carbon first. Probably one of the ways it does that is by hydrogen bonding with the carbonyl oxygen to make the carbon-oxygen bond more polarized, to make the carbonyl carbon more electrophilic. So that's what the enzyme wants to do. And if it does that, later on, we get that fully cross-linked horrible structure, which I drew once and then erased because it was too horrible, right? Okay. So you understand what the first step of what the enzyme is going to do. We're going to see that the beta-lactam is going to react with this negatively charged oxygen on the enzyme before it can even get here, thereby stopping bacterial cell wall synthesis, cross-linking. Then the bacteria have weaker cell walls, and they're easy for your immune system to kill and to clear. All right. Anything you want to ask about that? Yeah, go ahead.
Wait, so doesn't the strength or the struts, I guess, that you talked about, doesn't that come from the nucleophile on another one of those?
Yes, yeah, the cross-links come from the nucleophile on another chain.
So does the enzyme then inhibit that?
No, I think you misunderstand. The enzyme, I told you that this isn't a good leaving group.
Yeah.
What you're asking is what is the enzyme actually doing?
Yeah.
And I will answer that just briefly. I hope I can use the undo key. The enzyme's ultimately going to do a substitution reaction to become here. Now, notice that that is an ester and not an amide. Yeah, more reactive, right? And so now the second molecule can come in and do nucleophilic attack better. Yeah. So, okay, good. So anyway, this is but the first step in the enzyme doing its job. Now, let's show you what happens when enzyme meets amoxicillin. So we're going to put amoxicillin here. Oops, no. We circled but forgot to press copy. There. Copy. Now, what is not immediately apparent to you or to me is that as far as the enzyme is concerned, the beta-lactam looks like this. Now, you don't see those structural similarities, and in part that's because we've just drawn this two-dimensionally. You're not seeing the structure. But the beta-lactam actually fills the enzyme active site and binds exactly where this section of the peptidoglycan does. And in fact, a big area of drug development in over the past 50 years has been designing molecules that fit better in enzyme active sites than the things that are supposed to go in there in the first place. So you'll have to accept maybe on my word that this binds in the enzyme active site and actually looks like, to the enzyme, looks like this portion. You can see maybe where we're going, the nucleophile in the enzyme will now attack the carbonyl carbon of the beta-lactam. And that beta-lactam, as we have said, is essentially spring-loaded because of ring strain. So I'm going to now abbreviate some of the beta-lactam structure. For example, this is just going to be NHR. It looks like I missed the nitrogen. There it is. We'll draw the 5-membered ring because we like pentagons. And this portion. All right, and then I'm just going to draw a smaller version, unlabeled, let's see, of the enzyme. So here's the nucleophile that did the attacking. Here's the negatively charged oxygen and the tetrahedral intermediate. Here's what's going to be the leaving group. And what we're going to do next is electrons kick down, leaving group leaves. We typically wouldn't expect a negatively charged nitrogen to leave. Ring strain is going to pay for that. The other thing that's going to help it happen is it's going to pick up a proton, probably from the enzyme as it leaves. We're not going to worry too much about, nope, we don't want that to happen. We're not going to worry too much about what that acid is. It's probably a functional group on the enzyme, but since we're not focused on it, this is fine. The nitrogen picks up a proton as it's leaving, and let's draw the product that comes from that. You'll notice that we no longer have a 4-membered ring, and therefore the bonds of the atoms in that, what used to be that 4-membered ring, are free to rotate and adjust to achieve much more favorable conformations. Here is now the carbonyl oxygen and the carbonyl carbon. Here is the oxygen from the enzyme. It's now an ester oxygen, and here is the enzyme, which we'll color. Effectively, the enzyme acted as a nucleophile, attacked the carbonyl carbon. We got a tetrahedral intermediate, and then the leaving group left. I'll highlight the leaving group in yellow, sorry. And that's the substitution reaction. That's an acyl substitution reaction. The blue carbonyl carbon used to be bonded to the yellow nitrogen. Now it's bonded to the purple oxygen. Importantly, this, what we're going to call acylated enzyme, that is the nucleophile on the enzyme has been acylated, is inactive. It can't go on and catalyze the reaction it's supposed to react with, supposed to do, because the oxygen's no longer negatively charged. It's tied up in an ester. That bacterial glycopeptide transpeptidase is now dead, it's inactive, so you can't do the first step in cross-linking the cell walls, so cell walls are weaker. Yes?
I see how the cell walls, the peptidoglycan, wouldn't be able to come together. Would an additional peptidoglycan molecule come along and do carbonyl attack on the acylated enzyme and bind to it?
Yeah, so I don't know, it's a good question. Could a subsequent nucleophile hydrolyze this ester? I don't know how stable that ester is. Apparently it's stable enough, it doesn't hydrolyze at a rate that allows the bacteria to keep up with its cell wall synthesis demands. Sometimes in biology you don't need to totally shut down a process, you just need to slow it down. And this may be an example of that. Yeah. Okay, what else? Yeah.
Wait, I might have broke down the structure wrong, but where did the H in the RNH come from?
That's this part of the molecule abbreviated. So there was an N, an H, and then this R group.
Okay.
Yeah. Yeah. Different beta-lactam antibiotics will differ in the identity of the group, sort of out here. Now, you guys have heard of bacterial resistance to antibiotics, right? It's one of the reasons why when you go to the doctor and you have a sore throat, they kind of want you to wait a few days to really show that it's actually bacterial instead of viral. If it's viral, the antibiotics aren't going to help you. They don't do anything to viruses. And the more doctors prescribe antibiotics, the more bacteria have a chance to evolve mechanisms to be resistant to the antibiotics. There's a whole host of antibiotic resistance mechanisms, but one of them you can understand, and that is that bacteria can develop, and there are enzymes that exist now that are called beta-lactamases. And the job of the beta-lactamase is to hydrolyze the beta-lactam before it can acylate the transpeptidase enzyme that does the bacterial cell wall synthesis. So in a way, bacteria are taking advantage of the thing that makes the antibiotic effective in the first place, which is the ring strain. They've developed an enzyme that simply hydrolyzes that, gets rid of the ring, and then it's no longer a good electrophile. All right. Anything more we need to say about that? Yeah.
So it just basically breaks up the ring before it.
Yeah. Yeah, the beta-lactamases would hydrolyze this ring. So what that would look like is basically this same reaction, only the nucleophile would be water. And in the end, you'd have an OH here. And that hydrolyzed beta-lactam is no longer reactive. All right. So it's going to get worse before it gets better in terms of the complexity of what we're drawing. You thought this was bad. That actually may be the worst thing we've drawn today. But there will be other bad moments. So we're now going to talk about acyl phosphates as acylation agents and also thioesters. You have seen these before. We've talked about them. So this, at this point, should be something of a review. A thioester has a carbonyl carbon that's attached to a carbonyl oxygen, and then the yellow group is a thiol, or is a thiol group. I don't know what I'm getting ahead of myself. We'll just put R here. A sulfur bonded to some other alkyl group. The leaving group for a thioester is Sr minus. And this is a decent leaving group. It is not as good of a leaving group as chloride, but you can tell it's an okay leaving group because its conjugate acid, the thiol, has a pKa of around 8. So that means that the thiolate, the negatively charged sulfur, is a much better leaving group than, say, hydroxide or OH or OR minus. Similarly, you have seen before acyl phosphates, which I'll draw again now. In the acyl phosphate, the yellow group is a phosphate group. I'm going to draw it in this particular protonation state. Some people will draw it with a negatively charged oxygen there. Either of those is fine. Again, here's the carbonyl carbon, carbonyl oxygen, and here's the yellow leaving group. There's another class of acyl phosphates in which the OH group over on the right-hand side is going to be bonded to a carbon and some other stuff. We'll just call that OR. But they essentially have the same chemical features. We'll call them acylating agents because they've got something on them, the yellow thing, which is a decent leaving group. So in both of these cases, the leaving group is the dianion that would look like either of these things. And based on what we talked about in chapter 15, the conjugate acid of the dianion is the monoanion. And this is review, this is not new, but the pKa of both of those conjugate acids is 7. So you predict both of these to be decent leaving groups, and in fact, you predict the acyl phosphates to have a slightly, maybe 10 times more decenter leaving group than the thioester. Nature uses acyl phosphates and thioesters to make more stable carbonyl compounds. So understand, and you already know this from what you've learned in chapter 16, it's pretty trivial to start with a more reactive carbonyl compound that has a better leaving group on it and use a nucleophile to get to a less reactive carbonyl compound that has a less good leaving group on it. You're going to see biology do that all the time. So we will see biology turn acyl phosphates into thioesters. That's downhill, right? Because the thioester leaving group is not as good of a leaving group as the phosphate leaving group. And we will see nature use thioesters to make amides and esters. Yes?
What's the pKa of the thiolate?
The pKa of, yeah, that's 8. Yep. Sorry, I can't write clearly, so. Decipher my ancient handwriting, yeah. Is handwriting going to go away? Are they going to eventually stop teaching us to write with pencils? We'll just type the whole time? Nah, all right. I don't know, 2-year-olds, if you've seen 2-year-olds with devices, they know how to swipe better than, yeah. Okay, yeah. I don't have any strong opinions about cursive. I know some people do, but. Okay, so let's do some reactions involving acyl phosphates and thioesters as leaving groups. So this example comes from the synthesis of the amino acid glutamine. You start out with the following 2 functional groups that aren't going to change over the course of the reaction. And then we get to the part of the molecule that is. And here is the acyl phosphate leaving group. So here's the carbonyl carbon, there's the carbonyl oxygen, and there's the leaving group. Nature is going to use ammonia as the nucleophile, though it's going to have to transport that from some other source and release it. It's not like you have a lot of ammonia in your blood. That nitrogen is going to act as a nucleophile to attack the carbonyl carbon. Probably that the enzyme that catalyzes this reaction will either protonate that oxygen before or during, or at least hydrogen bond with the oxygen while the nucleophile is attacking. I'm going to skip several steps ahead in the mechanism. I'm also not going to show the proton transfer reactions, but I will show the key tetrahedral intermediate, which looks like this. Here's what used to be the carbonyl carbon. Here's the carbonyl oxygen. Here is the nucleophile that came in. A proton has been removed so that now it's a neutral NH2 and not a good leaving group. And then here is the phosphate group, which is going to be our leaving group. Here the phosphate is a much better leaving group than than the NH2. So electrons kick down and leaving group leaves. And then what you're left with is the amino acid glutamine. So this is one way. The identity, well, anyway, sorry. I'm going to say something, then decided not to. So look at, you can recognize this as a substitution reaction because the acyl group, the carbonyl carbon and the carbonyl oxygen, have swapped out what their leaving group is. And we can draw that leaving group here to make the substitution point a little bit clearer. Notice you've gone from something that is more reactive, an acyl phosphate, to an amide that is less reactive. So this is downhill in energy, and it's very efficient. Okay. Another example is a little tricky. It involves a more complicated acyl phosphate. So I told you that acyl phosphates sometimes have an OH group here and sometimes have an OR group. Now I'm going to show you an example where it's an OR group. And what I'll show you here is important in fatty acid biosynthesis. So nature will take a fatty acid and it will take ATP and it will use an enzyme, and I'm not going to show you this mechanism or even worry about it, to make the following. We'll deal with this later in our chapter on metabolism. It's going to make the following acyl phosphate. For now, it's enough to see that the carboxylate in this reaction is going to be the nucleophile and ATP will be the electrophile. That's a preview. We'll do that in a subsequent chapter. For now, we're going to focus on the structural properties of the acyl phosphate that gets made in this process. Here's the phosphorus, there's the oxygen, there's the negatively charged oxygen. Here is the OR group, only now we're going to draw it. So get ready, there's a 5-membered ring. OH is here and here. That 5-membered ring is called ribose. Then there's a wedge here and with a nitrogen. Okay, what we've just drawn is called an acyl AMP, where AMP stands for adenosine monophosphate. This group here is the nucleobase adenine, and that's A. Together, the adenine and the ribose ring make adenosine, and then the M and P stand for monophosphate. But for our purposes, if you relax your eyes a little bit, there's the carbonyl carbon, there's the carbonyl oxygen, and this is the leaving group. Now, you might look at these two reactions and wonder, what on earth is nature doing? Why not just use the phosphate? It's so much more efficient. And the answer is, enzymes in nature have to catalyze the right reactions, meaning the right molecules have to fit in the enzyme active site, and they should also not catalyze the wrong reactions. And in order to do that, the enzyme needs to bind with the target molecules very specifically. So at least some of what's going on here with this giant leaving group is we're providing a handle for the enzyme to hold on to recognize the right thing and not recognize the wrong thing. But once you realize that, if you can recognize this as an acyl phosphate that is a decent leaving group, then what we're going to do is pretty trivial. Okay, questions about this? Some people will abbreviate this as OAMP. And the point is, as I said, if you're got mixed emotions with overwhelm and boredom, that's exactly where you ought to be, because this is just an acylating agent. It's got a good leaving group on a carbonyl carbon. So what I'll show you now is how nature takes the acyl AMP and reacts it with a thioester, reacts it with a thiol to make a thioester. Often, the R group here is many, many, many carbons long. So I'm going to abbreviate the acyl AMP like this. And then the nucleophile in the next reaction is going to be a thiol, which is great. But you'll notice I've left a lot of space over to the right, and that is because this thiol is like unnecessarily complicated. So here we go. There's 2 carbons and a nitrogen, an amide bond, another 2 carbons and another nitrogen, and then another amide bond, and then an oxygen, and on the neighboring carbon, let's just put 2 methyl groups, just because, and then an oxygen here, then a phosphate, then another phosphate, and I'm running out of space, then a ribose ring. It just keeps going. A wedge there, and then an adenine base, which I'm going to abbreviate with the letter A. This whole horrible thing is called coenzyme A. And fortunately, people will abbreviate it even further, and they'll just put an SH with a line to CoA, and assume that if you want to know what the heck CoA is, you can just look it up. I don't have it memorized either. Again, why would nature bother with this huge, long chain of atoms between adenine and the thiol? Again, that's probably a handle that the enzyme holds on to get the thiol into the right place. And you can learn more about that in biochemistry. But for our purposes, we'll show the reaction basically as follows. Here is the coenzyme A thiol. Probably a base from an enzyme removes the proton first, so it can be the nucleophilic thiolate. Then that negatively charged nucleophile can attack the carbonyl carbon of our acyl AMP molecule. The intermediate that gets generated is just the expected tetrahedral intermediate with the negatively charged oxygen. Here's the carbonyl carbon. Here's the new nucleophile that we formed our new carbon-carbon bond with. And then here is the AMP leaving group, which then electrons kick down, we form a new bond, a new pi bond, and the AMP group leaves, and we've just made the coenzyme A thioester. And then I'm just going to abbreviate the AMP leaving group like this. You would be able to draw it. It's just if you take this yellow portion and put a negative charge on the oxygen on the end and get rid of the acyl group, that's what the AMP leaving group looks like. So that's the substitution reaction. We've swapped out the coenzyme A thiol in place of the AMP leaving group. And that's downhill in energy because remember the AMP leaving group's a better leaving group than the thiol. Okay, so why would nature tune down the reactivity of a thiol? Turns out thioesters are pretty useful because they can be transported without hydrolyzing. Yeah, do you have a question?
Is there a strategy for recognizing where we're going to find the nucleophile on this? Because I feel like I'm capable of doing the acyl substitution if I can figure out what I'm starting with. But
Right. Right, so if you were looking at coenzyme A, are you saying, how would I know that the sulfur is more nucleophilic than like this oxygen?
Or like we've been dealing with like ketones like this whole time. How do I know I'm not going to backside attack that with something else?
Right, so a couple of things. You'll notice there are carbonyls here. Those are amides. And amides are not very reactive unless they're strained, as in a beta-lactam. So that's why for the most part you can ignore amides when you've got a nucleophile unless you've got an enzyme whose job it is to hydrolyze amides. So I'm not worried about these amide bonds because I know they're more stable than this particular bond here. Second, the best nucleophile. Well, these amide nitrogens are not nucleophilic. They're tied up in resonance with the adjacent carbonyls. This OH group is not as good of a nucleophile as the sulfur. I just know that by experience. Fortunately for you, most of the time it's going to be drawn like this, where everything you should ignore is abbreviated. Yep. Okay. So let's do a couple of reactions of thioesters. One of them is important in generating a neurotransmitter. So here is a thioester made from acetyl-CoA. We were made from coenzyme A and an acetyl group. It's called acetyl-CoA. We will learn where that comes from metabolically in a month or two, maybe more like a month. It's going to react with the oxygen on this molecule that's called choline. Now, as I look at that molecule, it's got a nitrogen that's attached to 4 alkyl groups. There's no lone pair on the nitrogen. So the only thing that can be a nucleophile is this oxygen. Here's the carbonyl carbon, there's the oxygen, and now our thiol is going to be the leaving group. And the enzyme that does this reaction will allow the oxygen to attack the carbonyl carbon, either by protonating the carbonyl oxygen first or by deprotonating the OH either before or while it attacks. In the end, what you're going to have is a new ester bond between the oxygen of choline and the carbon of the acetyl group, and the resulting molecule is called acetylcholine. And you may have heard about that before. That is an enzyme, that is a neurotransmitter. Interestingly, there are other enzymes that exist that hydrolyze the ester bond in acetylcholine to degrade the neurotransmitter signal. Yes?
If we are to deprotonate the alcohol on choline, what keeps it from doing intermolecular reaction, interacting with oxygen?
So are you imagining this, a negatively charged oxygen kicking this off as a leaving group? I think that sounds reasonable. Only you'd be making a strained 3-membered ring. Such things are known, but you need pretty good leaving groups to make that happen, and this probably isn't quite as good as that. The other thing is that the enzyme is going to guide the OH to be very close to the carbonyl carbon. Yeah. Okay. So one more thioester reaction. This one's relevant for blood tests. So if you go in and get a doctor says, I need to measure your cholesterol, what they're actually looking for is not the cholesterol molecule itself, but cholesterol as packaged in what are called high and low density lipoprotein particles. You've heard of HDL and LDL, right? Those are pretty complicated. They involve some lipids and some proteins, and then a form of cholesterol that I'm going to show you here. That form of cholesterol is called a cholesterol ester. And that ought to give you a clue as to what we're going to do. Cholesterol has the following structure. Again, we're not into memorizing structures today. 6-membered ring with a oxygen on it. There's another 6-membered ring with a methyl group there. Another 6-membered ring here with a down proton. But now that's an up proton. And then a 5-membered ring here with a methyl group there and a down proton there. Okay, you get the point. That's cholesterol. And cholesterol has double character. It is mostly nonpolar, but it's got a polar head group. And that's why it gets incorporated pretty well into the lipid bilayer. The OH can be exposed to water, whereas the nonpolar group can be in the interior of the membrane. However, if you want to transport it in blood, that's bad, right? You don't want to put, you want a molecule that, anyway, you need to transport it in blood, you don't want to have a nonpolar portion that's exposed to solvent. So what nature does is it packages this in a lipoprotein particle. Before it does that, it needs to get rid of this polar OH group, and the way we're going to do that is acylate it. So nature takes a coenzyme A acyl group, where the R group here is a C16 to maybe C18 chain. overall even numbers of carbons. I should include the carbonyl carbon and all of that, but that's a detail that doesn't matter today. Again, you have a carbonyl carbon and a leaving group, and this oxygen is going to be the nucleophile. Nature will do the nucleophilic acyl substitution or acylation reaction, and all that does is it allows the polar OH group to be modified with a really non-polar acyl group. And now the entire molecule is nonpolar, so it gets packaged efficiently into the nonpolar interior of these HDL and LDL particles. And that's what gets carried around, and that's what people are measuring when they're looking for cholesterol in a blood test. Okay, so a lot of structural complexity, a lot of overwhelm, and a lot of boredom because this is just the same reaction again and again with the same tetrahedral intermediate. One thing I will say in all of these reactions is that in the fog of war, as I've said before, you will be tempted to do something like this, in which you have an acyl group with a good leaving group attached to it, and it's going to look maybe different than you've expected because of the structural complexity, and you will see a substitution product, and you're going to be asked sort of what mechanism is reasonable. And if you're not careful, you will look at that, you will see substitution product, and you will think, ooh, substitution reaction. I know how to do that. I learned how to do that in 351. That's simple. And you will draw this arrow or select the option that has that arrow, and you will be exactly wrong. And you will even see in your future in biochemistry textbooks, sometimes they will show you these arrows for a nucleophilic acyl substitution reaction, even though they know perfectly well there's a tetrahedral intermediate. They do that because they're feeling lazy. Slightly less good, slightly less bad, but I also hate, is this option where people are like, okay, I want to communicate to somebody that I know there's a tetrahedral intermediate, but I don't really want to draw it, so we're going to go whoop, and then back down, and then that one goes. I also hate that. So don't do that. You must draw the tetrahedral intermediate because there is excellent evidence that there is one. And enzymes have evolved to stabilize that tetrahedral intermediate. So don't make that mistake. Now, we got about 3 minutes left, so I will now open myself up to cross-examination about the exam. Go. Yes?
So for the biological mechanism you showed, the main idea is just acyl substitution of sulfur.
Yeah, for these biological mechanisms that we showed, the main idea is nucleophilic acyl substitution with a tetrahedral intermediate. Yes? Yes?
And just being able to recognize that, not memorizing structures or anything, just saying.
Today we are not memorizing structures. Yeah, just recognizing the reactivity pattern. Yes?
Some of the reactions with ATP in the study guide, it would be the alpha or the gamma phosphate
Yep.
group, and that would change the reaction. How do we know which one's a reaction?
So in the study guide, they actually do take you in this chapter through this step where ATP is modifying the carboxylate. I am saving that for a future date, so you don't have to worry about that. We'll have more to say about that. It just fits better, I decided on the fly this morning, in the metabolism chapter. Okay, next. Should you have finished study guide 16? Yeah, this completes it, so we're now caught up. Yes?
Do we have to draw any of the molecules?
Well, you have to draw any of the molecules. The exam's multiple choice, so you don't have to draw anything. That being said, you'll want scratch paper to work things out because it's generally not a winning strategy on my exam to just stare at it and try to eliminate options and then pick the best one that looks most reasonable in the moment. You'll want to actually bring a sheet of paper and draw things out, do mechanisms, whatever it takes to be successful, like you've done in the study guides and problem sets. Yes?
Can we write on the test?
You can write on the test. You can staple your scratch paper to the test. Yes? Others? 30 seconds. Nobody wants to ask what's on the test? Everything is on the test now. Boo! I know. But you've already said you hate me, so yes. Okay, as you're leaving in the last 5 seconds, the question was, what about stuff from 351? Your best bet on 351 material is to review it as you need it while you've been doing study guide problems.